Everyone, my name is Hao Chen. I'm a PhD student from UT Austin, and today I'm going to present our recent progress, reinforcement learning guided detail routing for custom circuits. Custom circuit design has become one major bottleneck in chip design, and one main reason is that the layout process remains heavily manual. And routing is one of the most intricate process doing custom layout. There are five main reasons that make custom routing so hard. First, custom circuits, it's complicated and sensitive, and that makes the layout of custom circuit very susceptible to parasitics. And we have very complicated design rules since we are dealing with transistors in custom layout. And we have layout constraint in order to satisfy performance. And also there's no convenient evaluation metrics. We need to consider noise, gain, voltage swings, etc. in the custom world. And there are often trade-offs between these metrics. Finally, we have something so-called design convention and aesthetic engineering. In addition to wireless optimization, the custom router needs to handle more design aspects such as current balancing and voltage drop. In the existing literature, there are template-based and simulation-based approaches, but the problem is that they suffer from poor scalability. Therefore, constraint routing that formulate design needs into various geometrical constraints is the most widely used technique, and since it's efficient. Common constraints include symmetry, topology matching, exact matching, etc. However, these algorithms are usually designed for specific use cases. And therefore, we want a constraint formulation with better flexibility and descriptiveness to cover all many real-world needs. Approach to solve path matching constraint that can cover real-world custom routing needs. First, a path is defined as a pin-to-pin connection within a net, and a path matching constraint specifies a group of paths that need to be matched. Note that path matching constraints are able to describe many widely used geometrical constraints. For example, symmetry constraints can also be described by extending path matching constraint with additional requirements like segment count and segment locations. And solving path matching constraints is hard. No previous work considered this new formulation. Also, there's a high probability that there are dependencies between different path matching constraints. Optimizing one constraint could affect the results of some other constraints, and RL could be a good candidate to solve this. Now let's introduce our RL-guided custom routing framework. First, let's see the state of the RL environment. Transform the routing solution of a group of nets to a heterogeneous graph with 3 node types and 4 edge types. Training on the heterogeneous graph, we initialize the feature of each node accordingly. We can talk about the action, transition, reward, and how we do the training. Given a state, the RL agent can pick a segment to remove and perform rip-up and reroute. Then, we'll get an adjusted routing solution and move to a new state. Or, the RL agent can return the termination signal and just stop the entire optimization process. Now I'm going to introduce the structure of our policy and value networks. Given a routing solution of a group of nets, we'll get the heterogeneous graph state representation first, then it'll go through a GNN and do feature aggregation on different nodes sequentially. After the aggregations, we'll get the segment embeddings. With the embeddings, we can calculate the average as the global representation and feed that to the value module to get the predicted state reward. Then we take all the segment embeddings and state embedding to the policy module to get the expected returns of actions. And finally, we can train the RL agent with the PPO algorithm. And now let's take a look at the reward function. In the custom routing problem, we have to consider some important objectives, including total wire length, total via count, total violations, and average peak-to-peak path persistence. Lastly, I'm going to introduce the proposed RL-guided rip-up and reroute scheme. The proposed scheme integrates train and RL policy to a rip-up and reroute optimization procedure. Started with randomly routed solutions, we can transform the routing to graphs and states. And our agent can decide which segment to remove and perform rip-up and reroute to adjust the routing topology. When our agent stops, We can further reset the history cost of the entire routing region since it opens up a new opportunity for the RO agent. By repeating several iterations of this procedure, we can get a more optimized result. Okay, for conclusion, in this work, we propose an RO-based custom detail routing framework uh, with efficient heterogeneous graph representation for solution modeling. And then we show that it's good at solving path matching constraint, and it's flexible to extend to new objectives by adjusting the reward function. And most importantly, it's generalizable. For future direction, we want to target more complicated custom routing strategies. Thank you.